Our class today is on slope deflection method of analysis. In our previous classes, we treated moment area method and consistent deformation method. But in today's class, we are to learn slope deflection method of analysis. This lecture note is presented by Chief Owus M. Ibarubulem Ugom Sinachi 1 of Umezegu, B. Eng. Civil Engineering, M. Eng. Structural Engineering, PhD, Structural Engineering. He is a reader of Civil Engineering, Federal University of Technology, Owerri. Slope deflection method is a method of structural analysis for determining the displacements of indeterminate structures. Unlike the other one we did earlier, constant deformation, in constant deformation we determine the reactions at the redundant supports. But in slope deflection methods, the first thing we shall determine are the displacements, which can be in form of deflection or rotation at the redundant supports, after which we go ahead to determine the reactions like support reactions and bending moments using the principle of equilibrium of forces. In structural analysis, we have two main categories: the displacement methods and the force methods. In displacement methods like slope deflection, the direct result of solving any simultaneous equation are the displacements, whereas in force method, the direct result of solving simultaneous equation are the forces. Today we are studying slope deflection, as I said earlier. A continuous beam with one sinking support shall be used to explain this method of analysis. On the screen, we see a beam that has 1, 2, 3, 4 supports, meaning that it has two redundant supports. But we are not going to use the approach we use in consistent deformation method. A different approach will be employed in this case. Support C of this beam sank through a deflection of delta from the original line. If only the second span of the beam is considered in the first instance, then drawing the portion will give the figure shown. This is span BC of the beam. Is a combination of a case that has end actions induced by transverse imposed loads AF and a case that has end actions induced by deformation of the beam through sinking of support. The total end action of the beam is the summation of the two cases. So even without a load, by mere sinking of the support, actions will be induced at the supports. Then even if the support is not sinking and load is on the beam, actions will also be induced on the supports, meaning that in this case the total action induced on the beam are the one due to the sinking of the supports or displacement of the supports, and the one due to the externally imposed loads, as we can see on the screen. The total action induced on the supports is denoted A and is equal to A subscript F plus A subscript D. A means moment, A means M for moment and Q for shear force. So that action can be moment or shear force. If it's moment, you denote it as M. If it is shear force, you denote it as Q. Then by the subscript F and D denotes the fixed end action, that is action at the support due to external applied loads, and D is the subscript denoting the action applied at the support due to sinking of the support. Equation 1 is the total action at the support due to external applied load and due to sinking of support. Then A can mean, as we said earlier, bending moment or shear force. The two cases are shown. In the first case, that is no sinking of support, the beam has external load, as you can see. Then this external load will induce shear forces and bending moments at the supports MF and QF at support 1 and at support 2. The second case is this one. There's no external loads on the beam. Rather, one of the supports sank, like support C sank through a distance of delta. This sinking of support made the beam to deform and induced bending moments and shear forces at the two ends of the beam, MD and QD, as we can see on this screen. If the end action is the moment, then equation 1 can be written as equation 3. We have M as the total moment induced on the support equals moment due to external applied load and moment due to sinking of support or yielding of support. If the end action is shear force, then equation 1 will be represented as shown on equation 4. That is total shear force on the support is shear force due to external applied loads and shear force due to sinking of support. The two basic equations of slope deflection methods are shown on equation 5 and equation 6. In this case, we are looking at two supports. Let me say support 1 and support 2. Then the span is span 1 and 2. In that case, at support 1, we have M12, and support 2, we have M21, considering span 1, 2. So M12 means supports in span 1, 2. M12 is moment at support 1 within span 1, 2, and is equal to MF12, that's fixed end moment at support 1 within span 1, 2, minus 2EI. I in this case is I, the second moment of inertia of span 1, 2, divided by L1, that is length of span 1, 2, or multiplied by, in brackets, 2 times theta 1. Theta 1 is the slope of the beam at support 1 plus theta 2, that's the slope of the beam at support 2, minus 3 over L12 times delta 1, 2, that is the difference between the support 1 and support 2 when one of the supports sank laterally. The same measure is applied on equation 6. In this case, equation 6 is M21, that is moment at support 2 within span 1, 2. The same thing we explained in equation 5 is also applicable to equation 6. But these two equations are the two basic equations of slope deflection method, and you must take it as handy as possible. If you like, you can memorize it. I think it's better that you memorize it because you're going to apply it in other spans. Equation 7 is the equation that can be used to calculate the shear force between a span when the moments are known. That's in this case moment not due to external applied load but due to sway or due to sinking of support. If the support sinks, the shear force can be calculated using that equation 7. Equations 8 and 9 are equations to calculate shear force, in this case not due to sway or due to sinking of the support, but due to the externally applied load. Whereas Q12 is the shear force at support 1 within span 1-2, and is equal to QF12, that is fixed end shear force due to externally applied load on support 1 within span 1-2, plus 6AI12 over LO12 squared in bracket theta 1 plus theta 2 minus 2 delta 12 all over LO12. I think I explained all these parameters while I was talking about the equation 5 and 6 for bending moment. Note, shear force at support B, in this case B is a support that has BC as a neighbor and BA as also the support B is lying between span BA or AB and span BC. Therefore, it takes some load from span AB and also some load from span BC. Hence, equation 10 is used to describe the total reaction at that support. That is cure BA plus cure BC. Equation 8 to 10 are used to calculate the shear forces. QF is the initial shear force before deformation. The table contains the formula for calculating fixed end shear force and fixed end bending moments. As you can see, this is a beam clamped at both ends. The fixed end shear forces at A and B are for A at support A QL over 2, at support B QL over 2. Whereas in this area, this is the formula to calculate the fixed end moments. For MFAB is minus QL square over 12. For MFBA is QL square over 12. But in this case, the two ends are not fixed. One end is fixed, the other end is propped. That's, you can call this a propped cantilever. The fixed end shear force at support A is 5QL over 8, whereas at support B is 3QL over 8. For body moment, at the fixed end, that's at support A, it is minus QL square over 8, and at support B, it is 0. It's also good to memorize this formula because you may stumble to the problem when this formula is not within reach. So better commit it to your memory so that whenever you are solving, you can easily bring it out from your memory and use it to solve your problems. The formula for calculating the fixed end shear force and moment continues on this table. As I said earlier, you better commit it to your memory so that you will not easily forget it. But if you forget it, find somewhere in your diary and note it, but don't take it to the exam hall. Because if you take it to the exam hall, it will be exam malpractice. But I mean, when at your leisure or when you're doing any consultancy job, you can always find it and use. Application of the method. Principle of static equilibrium is very important in the slope deflection application. The following steps are taken. 1. For each span ij, write the two basic slope deflection equations as seen in equations 5 and 6. 2. Employ the condition of joint equilibrium. For example, MBA plus MBC must be 0. MCB plus MCD must be 0. MDC plus MDE must be 0, etc. and etc. That is, the moment at left hand of a support plus moment at the right hand of the support must always be 0. That is one of the compatibility equations, or I can call it the condition of equilibrium. If there is a sway, number 3 now, if there is a sway due to nodal sway force or by non-symmetry of the frame, the conditions of equation 7 is employed. For example, take the frame below. This frame has a sway load P. When you apply this load on this frame, it will swing to the right. That is sway. So in that case, you need to calculate the shear forces, in this shear forces, using that equation number 7 stated above. Principle of equilibrium has it that algebraic sum of horizontal forces is equal to 0. So in this case, if I add HA plus HD plus HE plus P, I must get 0. Step number 4. All the equations arising from steps 1 to 3 must, in bracket, not negotiable, be equal to the number of parameters required. When this is confirmed, the equations will be solved simultaneously. Step number 5. The value of the parameters from step 4 will be substituted into equations 5, 6, 8, and 9 to get the value of the joint moments and shears. In brackets, check also equation 10 for case of joints with multiple members connecting to it. Step 6. With the value of the joint moments and shears, any other reaction can be calculated using the principle of elastic equilibrium. Example 1. Determine the support reactions ROB and ROC of the beam shown using slope deflection method. Take EI to be constant. In this case, I can idealize EI for all the members to be 1. That is, for span AB, EI is 1. For span BC, EI is 1. For span CD, EI is 1. Then since there is no signal support, then the deltas, delta 1, 2, delta AB, delta BC, delta CD will be equal to 0. If there is signal support, then I have to use the value of that signal of support. But in this case, there's no signal support, then delta is 0. So in equations 5 and 6, then equation for shear force, where I have delta, I have to put 0 in their place. In this problem, I will employ the formula I showed you above for calculating the fixed end moments to calculate the fixed end moments. In this case, fixed end moments AB and DC are equal to 0 because those two ends are pinned. When the standard ends are pinned, the fixed end moment there will be equal to 0. MFBA QLO square over 8, when I calculated, I have 10.719 kilonewton. MFBC minus QLO square over 12, if I calculate it, I'll have minus 11.8125 kilonewton. MFCB equals the negative of MFBC, that is 11.812 kilonewton, and MFCD is minus QLO square over 8, giving us minus 26.469 kilonewton. The slope deflection basic equations for each span is accomplished here. For span AB, I have to write the MOAB and MBC from MAB. Since MAB is end support that is pinned, the moment there is 0. So MAB in this case equals 0. Then I'll write the equation for MAB. Then I said before, delta will be 0. So this delta will be 0. MFAB is also 0. That brings me to this equation. I'm solving. This is 0 equals 0 minus this. So in this case, for non-trivial solution, what I have in the bracket will be equal to 0. So solving the bracket, I'll have theta A equals minus 0.5 theta B, equation number 1. Then MBA, I write equation for it using that equation 6. Then substitute the fixed moments for MFBA. Then delta is 0. So wherever I say delta, I have 0. That's why you're not seeing delta here. Continue the solving. That gives me this. Simplifying further, I have MBA equals 10.719 minus 0.8571 theta B. I write it down. I go to span BC. I repeat the same procedure I did in span AB. So in this case, I write equation for MBC, substitute the parameters, simplify, and I got equation 3. I also calculated using equation 6 to get the MCB. out of the parameters and simplifying, I will get equation 4. I want to move into span CD. Using the first equation within span, I calculate M. Okay, in this case, using the second equation, that's equation for moment at the right, I calculate for MDC. Since moment at support D and D is the support at the end that is pinned to the moment there is 0, that's why I have equals 0. Delta is 0 because I'm not thinking of support. Then MFCD is also 0. That brings me to this. Then for non-trivial solution, the value in the bracket must be equal to 0. Then simplifying the bracket, I have delta D equals minus 0.5 theta C. That's equation number 5. Then for that span CD, the moment at the left support MCD, I did what I did earlier with other spans. After calculating, I arrive at MCD equals minus 26.469 minus 0.5455 theta C. So the first step has been concluded. I have to go to the second step. Second step is joint equilibrium. MBA plus MBC must be 0 and MCB plus MCD must be 0. Summation of the equations 2 and 3 gives 0. That is bringing equation 2 and bringing equation 3. If I add them together using that joint equilibrium condition, I will have what I have here as equation 7. Similarly, summing equation 4 and 6 to get 0 will bring me to equation 8. That's the end of step 2. I'll go to step 3. Step 3 is not applicable here because it is a beam with no sinking support and it is not a frame. So if it's a frame, I will consider it if it is now symmetrically or if it is having a swell load. But this is a beam, it's not a frame. And moreover, the beam has no sinking of support. So step number 3 is not applicable here. I'll go to step 4. Step 4 is satisfied because there are 6 equations for 6 moments. That is moment at support A. Support A has 1 moment. Support B has 2 moments, MBA and MBC. That's support C has 2 moments, MCB and MCD. Then support D has only 1 moment. So that's 6 moments, and we have already obtained our 6 equations. So we have satisfied step 4. Solving equations 7 and 8 simultaneously gives theta B equals 2.1428 and theta C equals minus 10.88. Step 5 is to substitute the values of theta B and theta C into equation 1 to 6 for the 6 parameters. Substituting theta B into equation 1 and solving gives theta A equals minus 1.0714. Substituting theta D into equation 5 gives theta C as 5.441. Substituting theta B into equation 2 gives MBA as 8.882 kilonewton meter. Substituting theta B and C into equations 3 and 4 gives MBC as minus 8.882 and MCB as 20.533 kilonewton meter. Substituting equation theta C into equation 6 gives MCD as minus 20.533 kilonewton meter. All the support moments have been determined. The support displacements have also been determined. The next thing is employ the equilibrium condition to get the support reactions. Taking moments about point B gives 0. That is RA times 3.5 minus 7 times 3.5 square over 2 plus MBA, all the moments just before point or support B, is 0. Solving this out will give arrow A to be 9.712 kilonewton. Ahead, we take moment about support C. That's determined just before support C. Just before support C, we'll get all the moments. Arrow A times in brackets 3.5 plus 4.5. That's arrow A times 8 plus arrow B times 4.5. Then minus that of uniform distributed loads. That is 7 times 8 square over 2. Then plus MCB. All these moments will give us 0. Simplifying, we have arrow B to be equal to 27.949 kilo. Finally, we take moments at point D, just before point D. That is arrow A times the total length plus arrow B times 4.5 plus 5.5. That's arrow B times 10. Then plus arrow C times 5.5. Then minus that of moment from the uniform distributed load. 7 times the entire length square, that is 13.5 square, all over 2. Then plus MDC. But this MDC is 0 anyway. So when we add them and equal to 0 and simplify, we arrive at arrow C equals 41.322 kilonewton. So if we've got all the vertical reactions apart from arrow D, then to get arrow D, we can employ the condition of summation of all the vertical forces will be equal to 0. That is arrow A plus arrow B plus arrow C plus arrow D minus the loads on the beam. That is 7 times 13.5. If we add them algebraically, we'll have 0. And simplifying, that gave us arrow D to be equal to 15.517 kilonewton. The reactions, that's vertical reactions and moments at the supports, are summarized as presented in the drawing or the diagram you can see here. This is arrow A now 9.712, arrow B 27.949, arrow C 41.321, arrow D 15.515. The moment MBA 8.882, moment MBC 8.882. So when you sum them algebraically, looking at the directions, you have 0. The same thing happens here. 20.533 and 20.533. Adding them algebraically will also give us 0. We look at another example. This example is a beam with 3 supports. That is one support is redundant. We also follow the same procedure we used in the first example. In this case, the question says no syncing of supports, meaning that delta AB and delta BC is equal to 0. And they say we should take EI as constant, means that EI for span AB is 1 and EI for span BC is also 1. As usual, we go to the table, pick the formula for fixed end moments, but MAB and MCB are all zeros since they are external or exterior supports that are pinned. So their moments and their fixed moments are all 0. So the only fixed moment I'm going to calculate is MFBA and MFBC, which calculated to be 6.75 and minus 18.75 respectively. The slope deflection basic equations for each span will be presented here. For span AB, we calculate MAB is 0. That delta is also 0. When you resolve, we have equation 1, that's theta A equals minus 0.5 theta B. We now solve for moment at the right support, that's MBA. As usual, when you simplify, you arrive at equation 2, that's MBA equals 6.75 minus theta B. For span BC, we calculate the moment at the left support, that's MCB, using the same approach. After simplifying, okay, sorry, I usually make this big. Since it's at the right side, I have to calculate the right moment first, that's MCB, so that I will be able to get the equation for theta C, since it's end support that is pin. After getting that, I will now do for the left support MBC. I have MBC as this, then substituting the value of theta C in terms of theta B and simplifying, I have equation 4. So at this point, we've done with step 1. So we go to step 2. Step 2 is about joint equilibrium. In this case, I have only one joint equilibrium, MBA plus MBC equals 0. So summing equation 2 and 4 will give us 0. So 0 equals equation 1 plus equation 2. When we add the two of them together and simplify, we're able to get theta B as minus 7.5. So that is the end of step 2. We go to step 3. In this case, step 3 is not applicable because it's a beam with no sinking of support and it's not a frame. We go to step 4. Step 4 is satisfied because there are 4 equations for 4 parameters: MAB, MBA, MBC, and MCD. These are the 4 parameters and you have 4 equations to solve. Theta B had already been determined as minus 7.5. So that takes us to the end of step 4. We enter step 5. Step 5 is to substitute the value of theta B into equations 1 to 4 of the 4 parameters. Substituting theta B into equation 1 gave us theta A as 3.75. Substituting theta B into equation 3 gave us theta C as 3.75. Substituting theta B into equation 2 gave us MBA as 8.882 kilonewton. Substituting I'm sorry, there is a mistake there. Let's start afresh. Substituting equation B into equation 2 gave us value for MBA, that is 6.75 minus in brackets minus 7.5, that is giving us 14.25 kilonewton meter. Substituting equation B into equation 4 gave us MBC as minus 14.25 kilonewton meter. Then we have got the moment because MAB and MCB are zeros because they are end supports that are pinned. So we've got the 4 moments: MBA 0, MAB 0, MBA 14.25, MBC minus 14.25, and MCB 0. The next thing is to calculate the vertical support reactions. Taking moment about point B gives 0. That is RA times 3 minus the UDL 6 times 3 square over 2 plus MBA, that's just before the support B, MBA, add it there. So when we resolve, we come down to 3 RA minus 3 times 9 because 6 over 2 is 3, 3 square is 9, plus MBA, which is 14.25, equals 0. Simplifying gave us RA as 4.25 kilonewton. Now, taking moment about point C will also give us 0. That is RA times 8, that is the total length, minus 6 times 8 square over 2, plus RB times 5, plus MCB. But MCB in this case is 0, but you still have to add it there. After simplifying, we got RB to be 31.6. Now, we've got RA and RB is remaining on the C. So we're going to use summation of vertical equilibrium of forces. That is RA plus RB plus RC minus the applied load will give us 0. After doing that and simplifying, we got ROC to be 12.1. On the screen is the summary of the bending moments and vertical reactions at the supports. At support A, there's no bending moment because it's an end support that is pinned. Moment there is 0, but the vertical reaction is 4.25 kilonewton. At support B, it has 2 moments, MBA and MBC, but total are equal. So summing them algebraically will give you 0. That's correct. At support C, okay, sorry, I said at support B, the vertical reaction there is 31.6. At support C is end support that is pinned, so moment there is 0, which is correct, and the vertical reaction there is 12.15. So this brings us to the end of the lecture. You can see it's quite interesting. It's not difficult at all. Just follow the steps as are enumerated. Simple calculations, and they are done. The beauty of this is we are able to get the displacements at the supports. We are also able to get the moments at the supports, and also able to get the vertical reactions. At this point, you can easily draw your bending moment diagram and draw your shear force diagram. So take time and watch the video over and over again, and probably take some problems on your own and solve to understand the principle. That brings us to the end of the lecture. I remain my humble self, Chief Owus M. Ibarubulem Ugomsinachi 1 of Umezegu, a reader of Civil Engineering, Federal University of Technology, Owerri. Bye bye. Bye.